All right, welcome to The Explainer. Today, we're not just talking about some abstract theory. We're diving into a full-blown cosmic cold case, a deep mystery that goes all the way back to the very first moments of our universe.
So let's start with the crime scene itself, our universe. When you actually look at the evidence, it's just so perfectly balanced, so finely tuned, that it almost feels impossible. Like, it seems like it just shouldn't exist. It completely defies any simple, oh, it was just an accident kind of explanation.
Okay, so take Exhibit A. We call it the horizon problem. Now you look at two regions on completely opposite sides of the sky, right? According to everything we know about the speed of light, there is no way, I mean zero way, they could have ever communicated, ever exchanged heat or information. But they have the exact same temperature. Think about that. It's like finding two total strangers born on opposite ends of the Earth and discovering they have identical fingerprints. It just makes no sense. It shouldn't be possible.
And then there's Exhibit B, the flatness problem. The geometry of spacetime on the grandest scales is incredibly, precisely flat. But here's the thing. General Relativity tells us that any tiny bit of curve at the beginning should have gotten way, way bigger over billions of years. Our universe should look like a crumpled ball or a warped saddle. Instead, it's like a perfectly smooth, flat sheet of paper. It just piles another layer of how is this possible onto the mystery.
So faced with all this impossible-seeming evidence, physicists came up with a prime suspect, a single idea, a single event that could potentially explain everything. And that idea is called cosmic inflation. And when we say brief, we really, really mean it. This wasn't some slow, lazy expansion. No, this was an unbelievable, explosive growth spurt. We're talking about taking a piece of space smaller than a proton and blowing it up to cosmic size. And all of this happened in a tiny, tiny fraction of the very first second of existence. It's just mind-boggling.
And what's so beautiful about this idea, so elegant, is that it seems to solve all of our problems in one fell swoop. See, that tiny little patch of space was all connected, all the same temperature. So when it blew up, it just stretched that uniform temperature across the entire cosmos. Boom, horizon problem solved. And that same insane expansion, it stretched out any curve so much that the universe became flat. Boom, flatness problem solved. It even gets rid of some weird exotic particles that the Big Bang predicts but we never see. That's the monopole problem. I mean, it's just an incredibly neat and tidy solution.
But here's the thing about a really good scientific theory. It doesn't just explain old mysteries. It has to make new, testable predictions. And inflation did just that. It made very specific claims about what the afterglow of the Big Bang, what we call the cosmic microwave background, should look like. It predicted the exact pattern, the statistical nature of these tiny little temperature ripples from that very first moment.
And guess what? The evidence that came in was, well, it was powerful. Over decades, we sent up a whole series of space telescopes, COBE, then WOMAP, and then Planck. And each one, with better and better precision, looked at that afterglow. And they found exactly what inflation said they would find. The data was a stunning, perfect match.
So, case closed, right? I mean, with that kind of evidence, you'd think it's a slam dunk. We found our culprit. But not so fast. This is where the story takes a sharp turn. Because when you look really closely at our prime suspect, you start to find some serious holes in its alibi.
Here's the problem. Our best theory of gravity, Einstein's general relativity, it's totally cool with inflation. It says, sure, this could happen, but that's all it says. It gives us absolutely no trigger for it to start, no way to control it while it's happening, and no mechanism to make it stop. You basically have to build the whole thing and put it into the theory by hand.
And the cracks in the case get even deeper. A lot of these inflation models lead to this wild idea of a multiverse with infinite pocket universes, which sounds cool, but it's something we can probably never test. On top of that, the theory itself often needs really specific, fine-tuned conditions just to get going in the first place. And it's become so flexible with so many different versions that some physicists are starting to worry that you can't ever prove it wrong, which is a big red flag in science.
And at the heart of it all is this mysterious, unidentified accomplice, a hypothetical energy field they call the inflaton. This is supposedly the thing that drove the whole expansion. But let's compare it to something real like the Higgs boson. The Higgs was a required part of our standard model of physics. The inflaton? Nope, it's just an add-on. We've actually observed the Higgs particle. The inflaton? Not a trace.
So this complete lack of a solid foundation, either in theory or in experiment, makes a lot of physicists really, really uncomfortable.
To its critics, the inflatron feels less like a real piece of nature and more like the old idea of the ether from the 19th century. A fudge factor, a placeholder we just invented to make the math work.
And this whole debate has basically split the physics community right down the middle. You can see this split perfectly in two of the field's giants, Leonard Susskind and Sir Roger Penrose. Susskind is the pragmatist. He says, look, inflation works. It explains what we see, so let's use it, even if it means accepting a messy multiverse. But then you have Penrose, the purist. To him, inflation is just an ugly patch on a deeper problem. He's searching for a new, more elegant law of physics that explains why the universe had to be this way from the start.
So you see, this is so much more than just an argument about data or the early universe. This is a profound clash of philosophies. It's a debate about the very soul of physics itself. What should a scientific explanation even look like? Is it good enough for a theory to just describe what's possible, or does it need to tell us why it had to be this way?
And that leaves us with a really big, lingering question, one that goes way beyond cosmology. What do we actually demand from physics? Are we just trying to find an explanation for what's allowed to happen? Or are we looking for an explanation for what had to happen? I mean, think about it. The answer to that question is going to shape the entire future of how we try to understand our reality.